Welcome to AI Frontiers, where we explore the cutting-edge developments shaping artificial intelligence and computer science. Today, we're diving into 12 groundbreaking research papers that reveal how AI is revolutionizing software engineering. These papers, all published on May 29, 2025, showcase a field in rapid transformation where traditional programming practices are being reimagined through artificial intelligence, quantum computing, and advanced automation. Picture this scenario. You're a software engineer working late into the night, wrestling with a performance bottleneck that's been plaguing your application for weeks. You've tried every optimization trick in the book, but nothing seems to work. Now imagine having an AI assistant that could not only identify the exact source of the problem, but also generate multiple optimized solutions in seconds. Sound like science fiction? Well, that future might be closer than you think. But as we'll discover today, it's also more complicated than we initially imagined. Today's research reveals surprising gaps between the promise of AI-powered development and current performance realities. Our exploration reveals a field undergoing revolutionary change. Traditional programming practices are being reimagined through the lens of artificial intelligence, while quantum computing opens entirely new optimization frontiers. Advanced automation is transforming testing and quality assurance methodologies. We're witnessing a renaissance in software engineering research, where sophisticated evaluation methods ensure that progress is genuine and meaningful. This journey takes us through remarkable successes, unexpected failures, and emerging opportunities that are reshaping one of the most important disciplines in computer science. Think of software engineering as the architecture of the digital world. Just as civil engineers design bridges and buildings that must withstand natural forces while serving human needs, software engineers create digital structures that must handle millions of users, process vast amounts of data, and operate reliably 24 hours a day, 7 days a week. Unlike physical structures, however, software systems are infinitely malleable and constantly evolving. This holistic discipline addresses the entire life cycle of software systems, from initial conception through deployment and long-term maintenance. What makes software engineering particularly fascinating is its intersection of technical rigor and human creativity, where engineers must balance competing demands while innovating within technical constraints. The field has reached a critical juncture where traditional approaches are being challenged by new paradigms. The first major theme emerging from our research analysis focuses on AI agents as master craftsmen in software development. Imagine having an intelligent collaborator that never sleeps, never gets tired, and can analyze millions of lines of code in seconds. These AI agents go far beyond simple code completion tools, acting as sophisticated systems that understand project context and make complex decisions about software design and optimization. They learn patterns and best practices from millions of software projects, with the potential to reduce optimization time from weeks to hours. However, reality presents a more complex picture. Current AI agents struggle significantly with challenging optimization tasks, achieving success rates below 5% on complex problems. They tend to focus on obvious surface-level improvements rather than fundamental algorithmic changes that could provide dramatic performance gains. This gap between promise and reality highlights the need for more sophisticated approaches. Our second theme explores quantum computing applications, representing a completely new frontier in software engineering. Think of quantum computing as having a master key that can unlock doors classical computers can't even see. Quantum algorithms leverage properties like superposition and entanglement to explore solution spaces in ways that classical computers cannot match. For software engineering problems involved complex optimization or searching through vast possibilities, quantum approaches could provide exponential speedups. Researchers are exploring quantum-enhanced approaches to test case selection, static analysis, code clone detection, and defect prediction. These applications take advantage of quantum computing's ability to process multiple possibilities simultaneously, potentially solving problems that are intractable for classical computers. However, this theme also highlights the early stage of quantum computing in practical applications, with most approaches remaining theoretical or experimental, and significant challenges in making them practical for everyday software engineering tasks. The third theme focuses on automated testing and quality assurance, where AI enables more sophisticated approaches to ensuring software reliability. Traditional testing often feels like looking for a needle in a haystack, checking specific scenarios while hoping to catch edge cases. Modern AI-powered testing is more like having a detective that can systematically explore all possible scenarios and predict where problems might lurk. Property-based testing represents a significant evolution in this area. Instead of testing specific input-output pairs, these systems verify that software maintains certain properties across a wide range of conditions. AI systems can automatically extract properties from code and documentation, then generate test cases that attempt to violate these properties. This approach is particularly valuable for cyber-physical systems, where software interacts with physical components and safety is paramount. The shift from specific test cases to general property verification enhances reliability through comprehensive scenario exploration. Our analysis reveals several groundbreaking findings, starting with the efficiency coverage paradox in requirement solicitation. Picture a detective trying to solve a complex case. They could interview witnesses individually for detailed information, survey the entire neighborhood for broader perspectives, or gather everyone for group discussion. Each approach yields different types and qualities of information. Research revealed that interviews are the most efficient method for capturing distinct user needs per unit of time invested, while surveys can capture the broadest range of needs, but with high redundancy. Focus groups fall somewhere in between, offering rich discussion but potentially missing individual perspectives. Perhaps most surprisingly, the research found that delaying the introduction of structured taxonomies during requirement solicitation actually results in more diverse and comprehensive requirements. This challenges conventional wisdom that providing structure early is always beneficial. Instead, allowing for open-ended exploration initially, followed by structured analysis, leads to better outcomes. Among all the fascinating research we've examined, one paper stands out as particularly illuminating about the current state and future potential of AI in software engineering. The study by Chan and colleagues tackles a fundamental question. Can we simply provide more computational resources to AI agents to make them perform better on complex tasks? The researchers developed a comprehensive evaluation framework using challenging software optimization tasks drawn from real-world repositories. These weren't toy problems, but genuine performance bottlenecks that human developers had encountered in production systems. The experimental design was elegant yet comprehensive, taking state-of-the-art AI agents and providing them with varying amounts of computational resources during inference, including multiple attempts, additional context, and execution feedback for iterative improvement. What the researchers discovered was both sobering and enlightening. Even when provided with significantly more computational resources, AI agents achieved less than 5% success rate on challenging optimization tasks. This performance remained consistently low across different problem types, programming languages, and agent architectures. The additional computational resources led to some improvements, but these were marginal compared to dramatic gains that might have been expected. The researchers conducted detailed analyses to understand why agents were failing, identifying several key failure modes that explain the performance gap. Most significantly, they discovered a plateau effect, where beyond a certain point, providing more computation time or attempts didn't lead to better solutions. This suggests fundamental limitations aren't simply about having enough time to explore solution space, but about agents' ability to understand and reason about complex software systems. The detailed failure analysis revealed 3 critical limitations, explaining why AI agents struggle compared to human developers. First, agents struggled significantly with low-level programming languages and systems-level optimization. While they could handle high-level algorithmic changes reasonably well, they had difficulty understanding nuances of memory management, compiler optimizations, and hardware-specific performance characteristics. This suggests current AI agents lack the deep systems knowledge that experienced human developers possess. Second, agents exhibited lazy optimization strategies focusing on obvious surface-level improvements like removing redundant calculations rather than identifying fundamental algorithmic inefficiencies that could yield dramatic improvements. Third, agents had significant difficulty with performance bottleneck localization. Even when provided with profiling information and execution traces, they struggled to accurately identify root causes of performance problems in complex code bases, which is crucial since effective optimization requires understanding not just what is slow, but why it's slow. Looking toward the future, the research points towards human-AI collaboration rather than replacement. Think of this as a symphony where each instrument plays to its strengths rather than trying to replace the entire orchestra. AI tools can be valuable assistants for developers, providing code suggestions and automating routine tasks, but they're not yet capable of replacing human expertise for complex optimization and problem-solving tasks. The field needs fundamentally different AI approaches that can develop deeper understanding of software systems. Contamination-resistant evaluation is becoming standard practice, ensuring that performance improvements are genuine rather than artifacts of training data overlap. Quantum computing shows potential as hardware matures, particularly for optimization problems that classical computers struggle with. Integration of sophisticated memory and learning systems could help AI agents better leverage past experiences, though current research shows this remains challenging. Synthesizing our findings reveals a field in genuine transformation, where realistic expectations meet revolutionary potential. AI is indeed revolutionizing routine tasks in software development, providing valuable assistance with code completion, simple optimizations, and automated testing. However, humans remain essential for handling complexity, creative problem-solving, and deep system understanding. Quantum computing is laying the foundation for future breakthroughs, though practical applications remain largely theoretical. Evidence-based evaluation methods are ensuring that progress claims are substantiated by rigorous testing. Requirements engineering is benefiting from strategic combinations of different elicitation methods applied at appropriate stages. The call to action for the software engineering community is to embrace a nuanced view of AI capabilities, leveraging these tools where they excel, while maintaining human expertise for complex challenges. This balanced approach promises the most effective path forward for advancing software engineering practice. Before we conclude, it's important to acknowledge how this research synthesis was created and validated. The content was synthesized using Claude Sonnet 4 from Anthropic, with audio generated through DeepGram text-to-speech synthesis. Visual elements were created using Grok image generation capabilities. Human expert review was conducted to ensure accuracy and clarity of the technical content. While we strive for comprehensive coverage, some oversights may exist, and we encourage listeners to consult the original research papers for complete details. All references and source materials are provided in the episode description for those interested in deeper exploration of these fascinating developments in AI-powered software engineering. Thank you for joining us on AI Frontiers today. If you found this deep dive into AI-powered software engineering valuable, please subscribe for weekly episodes where we break down complex research into actionable insights. We cover the latest developments in machine learning, software engineering, quantum computing, and emerging technologies, providing expert analysis with practical implications for developers, researchers, and technology enthusiasts. Visit the AI Frontiers channel for complete research coverage and additional resources. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from Archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.